When an ocean wave hits a sea wall, most of the wave having nowhere to go, returns back to the ocean, and on its way back interacts with incoming waves. In a similar manner, when an electrical wave travels through a cable and encounters an open circuit, the wave reflects back to the source. Cables are mediums by which electrical signals are transferred from one point to another. A cable is usually constructed by two metallic conductors separated by an insulator. The impedance of a cable is the impedance between these conductors, and is fixed regardless of the length of the cable. A coaxial cable or a coax is comprised of a center conductor enclosed by a metallically shielded dielectric material, inside a plastic tubing. Cables are available in several characteristic impedances, each optimized for a specific application. For example, a 50 ohm coax is used in low-loss applications, and a 75 ohm coax for maximizing the power to the load. When a signal travels through a cable, it is undisturbed until it encounters an impedance change. The characteristic impedance of the cable and the load impedance determine what happens to the signal at the load. A higher load impedance reflects a part of the signal back to the source. There is no reflection when the load impedance is smaller than the impedance of the cable. However, smaller loads cause signal loss. An equal load impedance prevents signal reflection while delivering maximum amount of power to the load. An impedance mismatch can happen whenever the signal medium changes. For example, when the source is connected to the cable or at the load. These mismatches cause reflection and signal loss. In general, the source output impedance, cable characteristic impedance, and load impedance must be made equal for optimal performance. Impedance matching maximizes the power transfer to the load and eliminates signal reflection. A perfect impedance matching transfers half of the source power to the load. Adding a resistor in series with the source or the load, or using a termination resistor is a basic method to achieve impedance matching. This circuit matches the impedance of a signal generator with a source impedance of 50 ohms, and an oscilloscope with an input impedance of 1 megaohms, to a cable with a characteristic impedance of 75 ohms. When the signal wavelength becomes a significant portion of the cable length, without a proper termination, reflection distorts the signal. The reflected wave changes the amplitude of the signal throughout the cable. At the source, it acts like a load, which if not properly addressed, can damage the signal generator. At certain frequencies, the reflected wave interferes constructively with the signal. The resultant signal is referred to as a standing wave. To demonstrate the effect of an improper termination, let's connect the output of a signal generator with a source impedance of 50 ohms to one end of a coax, and connect the other end of the coax using a T-connector, to another cable. Keeping the amplitude of the signal fixed at 1.2 volts peak to peak, while increasing its frequency, we monitor the effect of the reflection through the cable using an oscilloscope with an input impedance of 1 megaohms. Channel 1 in yellow displays the signal at the end of the extension cable, and channel 2 in blue displays the signal at the T connection between the cables. Increasing the signal frequency affects reflection, and changes the amplitude of the resultant wave. With a 50 ohm termination, the effect of reflection becomes insignificant. The small variation of the signal at the connector is due to the slight impedance mismatch between the cables, source, load, and BNC connectors. Time domain reflectometry or TDR is a technique widely used to analyze cables. Instruments such as the Analog Arts ST985, based on the TDR concept, characterize the length, impedance, and other characteristics of a cable. Most TDR analyzers can also perform signal loss tests at various frequencies, for which the cable must be terminated appropriately to avoid reflection. A TDR consists of a pulse generator, a monitoring instrument device, and a DSP. Generally, in these instruments, the generator outputs a fast transition pulse. This pulse travels to the end of the cable and reflects back. But first it is divided by the voltage divider formed due to the source resistance and the cable impedance. The division factor is then calculated by the DSP to find the impedance of the cable. The divided signal travels through the cable at a fraction of the speed of light in vacuum. This fraction is referred to as the velocity factor of the cable. For a coax it is about 0.67. The time it takes for the signal to reach the end of the cable and reflect to the source, is used to calculate the length of the cable. Impedance matching maximizes the power transfer to the load and prevents reflection. Damaging a cable, by twisting, bending, or kinking, or placing improper signal connectors in the signal path cause an impedance mismatch resulting in reflection, and consequently less than ideal signal handling. Thank you for watching.